So we have 4 zombies. They're running a race. The graphs give each zombie's distance as a function of time. So distance is on the y-axis, time is on the x-axis. So what can you say about how long the race was? 5 miles. How do you know? Right. The highest that all of the zombies have a range. The graph has a range from 0 to 5. The highest point on the graph is 5 miles. Okay, so it seems like they all ran 5 miles. And then who won the race? They tied. Can you explain how you know that, Brian? Yeah, they all hit 5 miles at the 5-hour mark. So it's a 4-way tie. All right, so what is the average velocity of each zombie over the course of the race? 1 mile per hour, because all of them traveled 5 miles in 5 hours. So change in distance divided by change in time will give you average velocity. They all went 5 miles in 5 hours, 1 mile per hour average speed. All right, so what's the average velocity of each zombie over the first 2 hours? Rather than over 5, we're just going to take an average velocity over 2 hours. So let's look at Feynman here. Over 2 hours, just going to mark where he was at 2 hours. How far did he travel? 2 miles. So when we do Feynman's average velocity, change in distance over change in time, 2 miles in 2 hours, 1 mile per hour. All right, and then we go back and look at Hertz. Mark where he was after 2 hours. Looks like he traveled about 1.5 miles. Maybe my line is crooked. 1.4, maybe 1.4 miles in 2 hours. So Hertz, change in distance divided by change in time, 1.4 miles over 2 hours. What's that? 0.7 miles per hour. And Noether, 2 hours. Noether had traveled 2.6. Yeah. 2.6 miles over 2 hours. That's 1.3 miles per hour. And then lastly, Donk. 2.5 or 2.4 maybe. .2 miles per hour. Okay. So when was Noether running the fastest? So we look at Noether's graph. Do you guys recognize these names, by the way? A couple of them. They're all famous mathematicians slash scientists. Yeah. Noether is Emmy Noether. She's like one of the few very famous female mathematicians. I was gonna name my dog Emmy, but then we ended up getting a boy. Anyways, when was she running the very fastest? In the beginning. Who said that? Brian, how can you tell? How can you measure the slope of a curve, though? I mean, we've talked about the slope of a line in many classes. Kevin?
You can approximate it by just basically taking a small sample and drawing a straight line.
that connects them. Yeah. So that's a good way. A secant line, yes. Take 2 points over a small change in time and connect them. I made it over like half an hour, right? No, it doesn't matter, but you get the idea. So you can see what's happening is that these little line segments are getting less steep as time goes on. The very steepest line segment that I can draw is close to time 0. So that's where she's running the fastest. And let's look at Planck and see what his running strategy is. Okay, so how did he decide to run this race? Yeah, maybe even stopped, because looks like, you know, from here to here, he traveled very little distance, if any, at all. Right? So he went fast, took a break. So he started fast, but was slowing down, because you can see the line, these little secant lines are getting less steep. So he started fast, but slowed down, took a break, and then started running faster and faster and faster and faster to catch up to the other zombies. So he started fast, he slowed down to a stop, rested, and then sped up until the end. So we have a radar gun pointed at each zombie right at the instant t equals 3. See if we can figure out a strategy to estimate how fast each zombie was going at that instant. And if you've had calculus before, don't give it away. So I want to know at exactly t equals 3, how fast was each zombie traveling? Do you guys have a chance to discuss this one yet? No? Okay. All right, so let's look at Feynman. At t equals 3, I would like to know how fast Feynman is going. Can we answer it? A mile an hour, because Feynman is traveling at a constant speed of 1 mile per hour all the time. So at any given instant, we can say how fast he's going. That's pretty easy. So Feynman is 1 mile per hour because it's constant. Okay, let's look at Hertz. At t equals 3, I would like to know exactly how fast Hertz was moving at t equals 3. Uh-huh. So how do I know that that's going to tell me his speed? What does the tangent line have to do with his speed? Okay, so you're saying it has to do with slope, right? And because over here we use the slope of the line to do speed, right? And back when we said how can you tell when Emmy was traveling the fastest, we were looking at the slope of little tiny line segments. So it has to do with the slope of this curve at this point. But I still am not quite sure about the tangent line thing. Why is it the slope of the tangent line? Well, don't tell me about we don't know what a derivative is.
It's the average of all the closer to.
Okay. So I could find an average rate of change. I could find an average speed the same way we did over the 5 hours or the 2 hours. I could find the average speed over a very small interval. I could put another point, you know, very, very close and find the slope of that little tiny segment. And then I could just make that point get closer and closer and closer. to t equals 3. Just find average velocity, but over a very tiny time interval. And that will give me a pretty decent estimate of instantaneous velocity. So we would find average velocity over teeny tiny time interval. Right, so I would do change in distance over change in time, where change in time is close to 0, like 0.001 or something. So we could do that for each of them. Find average velocity over a teeny change in time. So what happens as I let that change in time get closer to 0? Here's just we'll call this time and distance. When I pick 2 points, say this one and this one, so this is my delta t here, and I draw a secant line that connects them, the slope of that secant line is the average rate of change, is the average velocity. Because it's your change in y over your change in x, change in distance over change in time, gives you average speed. And then if we let this point over here to the right move closer and closer to the point we're interested in, we get secant lines that look like this. And what do you think happens when it lands right on top of it? What kind of line do we have? The tangent line. The slope of the tangent line gives the instantaneous rate of change. So this is going to be a recurring theme. We're going to talk about this lots and lots and lots, many times. It's just the first time you're going to see this concept. All right, so let's suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, which is 450 meters above the ground. And we want to estimate the instantaneous velocity at time t equals 5. And this formula gives the height of a falling object after t seconds. It's just a formula from physics, which you probably will even derive in physics if you're taking it this semester. All right, so anybody had physics? Know what these constants represent? A is the acceleration due to gravity, and v naught, initial velocity, s naught, initial height. Yeah. Okay, so I'm going to just plug in the constants I know. Acceleration due to gravity, 32 feet per second, or 9.8 meters per second, whichever one you want to work with. They gave me my initial height in meters, so maybe we'll use the one that's in meters. Otherwise, we'd have to do some conversions. So 1/2 times 9.8 t squared plus my initial velocity. If I have a ball and I'm just holding it and I let it go, what's its initial velocity? 0, right? If I threw it downwards or I threw it up, it would have an initial velocity other than 0, but I just let it go. So that term is just going to go away because 0 times t is 0. And then s naught is 450. Okay, so s of t, simplify, half of 9.8 is 4.9. All right, and I want to find the instantaneous velocity at 5 seconds. Now, can I just plug 5 into this formula and get the instantaneous velocity? No, because what does this formula tell you? height. This formula doesn't tell you anything about velocity, right? So we have to be careful with what we're given and what we're asked for, particularly in calculus, right? Because it's very easy to fall into the trap, because in many math classes up until now, they give you a formula, they ask you a question, and the way you answer is you just plug into the formula, right? So this is a little bit different. We can't just plug in, because the formula they gave us is not a formula for velocity, it's a formula for height or distance. You can think of it as distance as well. All right, so if I want to know the speed at time t equals 5, how do we generally calculate speed? Distance over time, right? So I'm gonna find an average speed by calculating change in distance over change in time. Okay, so I want to know the speed right at 5 seconds. So maybe I could use what should I use as my interval, my time interval that I want to look at? Let's just get a rough estimate to start.
So you get to 5.
4.9 to 5. Okay, so on either side, that makes sense. 4.9 to 5.1. Okay, so let's get average velocity from t equals 4.9 to t equals 5.1. That seems like a reasonable thing to do to get a good estimate for the exact speed right at 5 seconds. So my change in time is going to be 0.2 seconds, right? 4.9 to 5.1 is 0.2 tenths of a second. And what's my change in distance over that interval? Yes, now we can plug in, because when you plug times into this formula, you get distance. So I'm going to use my calculator because I'm addicted to it, like we all are. All right, so I do this a lot because it helps you avoid typos and saves a little bit of time. So I'm going to put my s of t into my y equals 4.9x squared plus 450. There we go. I'm going to go to my home screen, and I'm going to evaluate that function at 4.9 and at 5.1. And I need to know the difference. I hit quit, second quit. So I was here. Anytime you want to get back to your home screen, you just quit. All right, so here's a quick little way that you can get your calculator to evaluate a function at a point. I'm going to put y1 there. Your calculator knows function notation, and my formula is written in the y1 spot. So the way you get y1 is the vars key, right? Vars, cursor over to y vars, choose function because we're working with functions right now. And then once you choose function, you get a list of all the y's. Choose y1 because that's where our function is. And then you just put parentheses 4.9. And that tells your calculator, plug 4.9 into y1. And then enter. Yep. And then rather than going through all that button pressing again, I'm just going to press second enter, and it calls up the previous thing that was typed. And I'm going to put in 5.1 now. Okay. So after 4.9 seconds, the height is 567.649. And after 5.1 seconds is 577.449. Distance traveled. So how far did it travel in between 4.9 and 5.1 seconds? Yeah, so we have to just subtract them. Oh yeah, okay. Oops. (9.8). So my change in distance is 9.8. Change in time is 0.2. And that comes out to what? 49 meters per second. Is this meters? This is seconds. All right, so that's a pretty good estimate. How could I get a better estimate? For the exact speed at right at t equals 5, the instantaneous speed at time t equals 5 seconds. How do you find the slope of the tangent line? Yeah, we could take time values even closer to 5. We could do 4.95 to 5.05, right? To get a better estimate, use a smaller time interval. Right, something like that. So the question asks us to estimate the instantaneous velocity. So, yeah.
Then you take those numbers, plug them back in, and get that number 2 for a tangent line.
That's not necessarily the tangent line. It's just a better estimate of the tangent line.
The comparison to the line between
the slope of the line.
The slope of the line.
Mm-hmm. No. So we're going to get two. So average velocity is always an estimate for instantaneous velocity. So here's an estimate, 49 meters per second. And then we could say not accurate enough. Get a better estimate by doing the whole process over again.
So you're playing with the decimal point.
Yeah.
For your more precise velocity.
Yes. So what I'm interested in is the instantaneous velocity at t equals 5. So I'm taking smaller and smaller time intervals around that point I'm interested in. Get better and better estimates. So if I drew a picture of it, so here's my, there's a picture, an estimated picture of what that 4.9 t squared plus 450 looks like. I'm interested in the instantaneous velocity at t equals 5. So what I did is, well, I started with 4.9 and 5.1, and I found the slope of the line between those two. And we said that's a pretty decent estimate of the tangent line, which is the instantaneous velocity. We said to get an even better estimate, make this interval smaller. Even better estimate of the tangent line. Just narrow in on that point you're interested in. All right, so I have to apologize for some of the graphs in your packet came out looking funny. I fixed it, and there's an updated packet in Moodle. So you just have to kind of bear with it. I think that this one's kind of okay. Yeah. Yes. Oh, did I miss something? Let me see here. Oh, no, thank you. Okay. So GSP 1.8 CN tower. Okay. All right, so here's a graph of my function that represents distance of the height of the ball after X seconds. And here's my fixed time 5 is what I'm interested in. So this secant line, the slope of this secant line, represents the average rate of change from this point to this point. From, let's see, I'll put it right on 0 to start. So from time 0 to time 5 seconds. The slope of this line, which is given right here, gives the velocity of the ball, the average velocity of the ball over that time interval. So what I'm going to do is make that time interval smaller and smaller by grabbing this point and moving it along. So as I make this time interval smaller, the slope of this line becomes more accurate at representing the instantaneous velocity at the fixed point. Okay? As these 2 points get closer together, this line approaches a tangent line, and when they're right on top of each other, it is a tangent line, and its slope is negative 49. We came up with 49 because we forgot the negative in front of the acceleration of gravity. But if we're talking speed instead of velocity, we got it right. Yeah, it's a nice animation, huh? You can come from the other side too. So we could find the average velocity from 5 to, this looks like about 9 seconds, and then move this point in towards the 5, and it approaches the tangent line. And when the 2 points are on top of each other, we have a tangent line whose slope is the instantaneous velocity.
But you can't find the height of the bounce. You know the way of the ball.
Right. So I should go back up here and let's see this. It should be negative, 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 negative. Okay. All right, so a good definition. A secant line is a line that goes through 2 points on a curve. Connects a point here to a point there, goes through 2 points. Now, a poor definition. A tangent line is a line that goes through 1 point on a curve. Why is it a poor definition? Yeah, it could, so it touches at that 1 point we're interested in, but it could extend and touch the graph somewhere else. So it might actually go through more than 1 point, but it's at the 1 point that we're interested in that it's just tangent, just touching. Yes, yep. So the graphical interpretation of average velocity is the slope of a secant line. Right? The slope of a secant line gives you average velocity. And the graphical interpretation of instantaneous velocity is what? Slope of a tangent line. So if we go back to the zombie graphs and draw a tangent line on each graph at t equals 3, that would be how we could calculate instantaneous velocity at time 3. If we have some way of calculating the slope of the tangent line. In this one, it's easy because the tangent line is the line itself. See, in this one, we could graphically estimate it. You know, we could go, well, we went over this much and up this much and try to estimate it if you drew it with a ruler carefully. This one's also tricky to estimate graphically. This one looks almost flat. So the slope of each of those lines gives each zombie's instantaneous velocity at time t equals 3. All right, so instead of finding a few average velocities and then making our best guess about what instantaneous velocity is at t equals 5, we could do things a little more formally. Okay, so the calculation for average velocity from the interval from 5 to t. So we're going to start at 5 seconds and go to just some time after 5 seconds. Okay, so t is just representing any time except t equals 5. So average velocity is always change in distance over change in time, delta s over delta t. So the way we find change in distance is you plug each of your times into the distance formula and subtract them, right? So my times are 5 and t, so I'm going to plug in s of t minus s of 5. That's just my change in distance. And my change in time is t minus 5. So s of t is negative 4.9 t squared plus 450, and s of 5, when you plug 5 in, you get 327.5. Subtract them over t minus 5, simplify, and we get this formula. So this formula gives you average velocity from t equals 5 to t equals anything, any other thing. Okay, so now that we know that this is the average velocity, we can use the table feature on our calculator to confirm the calculations we did earlier. So let's pull up the calculator. So in y equals, I'm going to put this formula that calculates average velocity into y1. So I know that this formula tells me average velocity between time t equals 5 and t equals anything else. So I'm going to go to the table and I'm going to plug in a bunch of different x's or t's to see the average velocity from 5 to varying other points in time. So I might plug in 5.2, 5.1, getting closer and closer to 5, right? 5.05, 5.01, 5.001, 5.0001. Yes. Oh, so first you go to table. Are you at your table? Okay. And you can't type in your X column? Just try typing something. No? Okay. Then you go to table set. It's right above window. And make sure independent is set to ask and dependent is set to auto. Yep. So if we go back to the table, what value for y, which represents average velocity, what value is y approaching as my x's get closer and closer to 5? Negative 49, which was what that graphical thing with the slider showed the slope of the tangent line being, negative 49. Okay. So it looks like this is approaching negative 49. We're going to talk about limits next class, but for now, the notation here makes sense. The way we write this is we say the limit as t approaches 5 of this expression, which represents average velocity from 5 to some other point in time, right? As we get closer and closer to time t equals 5, we are approaching negative 49. So the limit is negative 49. So now we're going to be even more general. We're going to replace the 5 with a generic t. We want to find the average velocity at any point in time. Oh no, sorry. We're still working with 5. So I'm going to replace the varying point. Instead of going from 5 to t, right? Instead of going from 5 to t, I'm going to go from 5 to some distance 5 plus h. So on this graph, what I'm doing, right, instead of having, this is my varying point, which we called a generic t comma s of t before, and we're using this fixed point 5 comma 327 and a half. Instead of calling this point t comma s of t, I'm going to drop this down here, this is 5. I'm going to call this point in time 5 plus h, which means what is my delta t? H. I went from 5 to 5 plus h, so my delta t is h. So I want to find the slope of this line, which is my average velocity. So the coordinates of this point are 5 plus h, comma what? S of 5 plus h. Yeah, because I'm calling this point in time 5 plus h, so that's what you plug into s to get the height. Yeah. Okay, so my average velocity is the slope of the secant line between this point and this point, from 5 comma 327.5 to 5 plus h comma s of 5 plus h. So we're going to do the exact same thing we just did. We're just changing the notation. Okay, and the purpose is your book uses both notations. Calculus switches back and forth between the two notations using whichever one is more convenient for the particular problem we're doing. All right, so I'm just showing you the same exact thing, two different notations. So now I'm going average velocity, change in s over change in time, and I'm going from 5 comma 327.5 to this point, 5 plus h, s of 5 plus h. I'm just finding the slope between those 2 points. So s of 5 plus h minus s of 5 over 5 plus h minus 5. So I plug 5 plus h into s, plug 5 into s. I'm just simplifying, and we end up with this. Again, this also represents average velocity. Okay? Average velocity from 5 to some other point in time, 5 plus h. So our new instantaneous velocity calculation, in our limit, earlier we were letting t approach 5 because we were using the point, we were going from time t equals 5 to t equals t. And so we let t equal 5, or t approach 5. Now we're going from t equals 5 to t equals 5 plus h. So to let the points approach each other, we let h go to 0. So we take the limit as h goes to 0 of this new expression that represents average velocity. It's the same thing, it's the same picture. I'm going to draw it one more time. So I've got this picture, something like this. Here's t equals 5. And here's some other point. We could call it t, a random t, or we could call it 5 plus h, some point to the right of 5. So we do it two ways. We can call it t, right? And then we find the slope between these two guys. And we take the limit as t approaches 5. Right? Or if we call this guy 5 plus h and find the exact same calculation, the slope of that line, change in distance over change in time, this time we take the limit as h approaches 0, because h is representing the distance between the 2 points. Yes, h can be negative so that we could approach from the other side. Yeah, it'll work both ways. Either way, you're just calculating a slope, just like the first algebra course you ever took. Calculating slope. All right, so instantaneous velocity of a function f of t at some generic point A, instead of using 5, we're going to use some point A, is calculated by taking a limit of f of a plus h minus f of a over h. So let me draw a picture of that one. So just be a little bit more generic. If we come back here and call these guys a's. Okay. Now we can calculate the instantaneous velocity at any point, not just 5. Okay, so the slope of those secant lines is going to be s of a plus h, right? Because this point right here is a plus h, comma s of a plus h, right? Because my input is a plus h, so my output is s of a plus h. And this point right here, its coordinates are a, comma s of a. So to find the slope, you just do change in y over change in x. S of a plus h minus s of a all over my change in x is just h. And then we let this expression change as h, the time interval, goes to 0. So that's where this comes from. F of a plus h minus f of a over h. And that's called the difference quotient of the function f. So when we talk about the slope of a curve, we mean the slope of the tangent line of that curve. And the slope of the tangent line represents instantaneous rate of change. If my graph happens to be representing distance and time, then it is velocity. The rate of change has a special name called velocity. Okay, so let's suppose Ian throws a grapefruit straight up with an initial velocity of 100 feet per second from a height of 6 feet. Without a calculator, let's find the velocity of the grapefruit 1 second into its flight. Let's see what's coming up here. Take a few minutes and think about it in your groups. A little less than 5 minutes left, so I'm going to go over this last question. So we end up taking the information given in the question and we write a formula for the height of the grapefruit after t seconds. Negative 16t squared plus 100t plus 6. So this is a function for height, right? And it's not a function for velocity, so I can't just plug in here. But velocity depends on the height of the ball. So I need this to calculate velocity. So I wrote down the formula for average velocity here, and I used ones, right? I want to find the velocity from some point between 1 and 1 plus h, time t equals 1 and a little after 1. So I calculate s of 1 plus h, which you get by plugging 1 plus h into your function for t. So we have negative 16 times 1 plus h squared plus 100 times 1 plus h plus 6, which should simplify to negative 16 times 1 plus 2h plus h squared plus 100 plus 100h plus 6. And I'm running out of room. Negative 16 minus 32h minus 16h squared plus 100 plus 100h plus 6. Okay. So this is just s of 1 plus h. And that's negative 16 plus 6 is negative 10. And I have a negative 16h squared. And, oh, I have a plus 100 too. Negative 10 plus 100 is 90. And negative 32h plus 100h is 68h. Okay, so there's my formula for S of 1 plus h. I need also S of 1. What do you get when you plug 1 into 90? Okay, good. So then I can, now that I have these done, I can calculate my velocity average. It's S of 1 plus h minus S of 1 all over h. So S of 1 plus h is just negative 16h squared plus 68h plus 90, and minus S of 1, which is minus 90, all over h. So the plus 90 and the minus 90 cancel. So I end up with negative 16h squared plus 68h over h. Does that simplify? Yep. Negative 16h plus 68. Right? That's my average velocity. Right? From 1 to some point a little after 1. Right? Now, what I want to calculate, though, is velocity instantaneous, which is what happens when we let the h go to 0. We let that distance between 1 and the point a little to the right of it get smaller and smaller and smaller. So I want to know what happens to the average velocity as h gets close to 0. Yeah, negative 16 times something that's getting super, super, super small. This product is getting super, super, super small. It is approaching 0. So I just am left with 68 feet per second. So it turns out I did not even need a calculator. I got the instantaneous velocity.